Okay, so we do all that in the last chapter, mainly just to apply it to this chapter. So the last chapter was good and all, but it's not so useful in the context of chemistry as a whole. So typically in chemistry, we're concerned with chemical reactions. And nothing we did last chapter was directly applied to a chemical reaction. We just looked at phase change, temperature change, kind of physical changes. So this chapter, we will take those things that we learned and apply those to chemical reactions. So we'll call this chapter either thermodynamics or thermochemistry, whatever you want to call it. But ultimately, it's taking what we learned last chapter and applying that to actual chemistry situations, chemical reactions. So a couple of terms before we get started, make sure we're on the same page. So calorimetry was what we did where we said heat lost equals heat gained, so Q lost equals Q gained. A calorimeter was the device that we used in class. So it's really just anything that insulates we can do chemistry in. So our calorimeters were those metal canisters with a styrofoam down inside. In lab tomorrow, we'll use just a styrofoam cup. It insulates fairly well. Then the word heat. The word heat is a term that describes what type of energy, total or average? Both. Total. And so heat describes total energy. So total energy is dependent on the amount of substance that you have, right? And at the same temperature, a big piece of something and a small piece of something, the big piece has more total energy. So if the amount depends, or the amount of heat depends on the amount of matter, we call that an extensive property. So an extensive property is just any property that is dependent on the amount of substance. So what's an example of another extensive property?
Weight.
That?
Weight.
Weight, yeah, so mass. Okay, so obviously the more of something you have, the more mass it's going to have, right? So a tiny piece of copper and a big piece of copper, the big piece has a greater mass. So heat was a measure of total energy. What is temperature a measure of? Yeah, average energy. So does average energy depend on amount? No. Temperature is independent of amount. So the word we have for being independent of amount is an intensive property. So what is an example of something or a property that is independent of the amount of the substance that you have? Well, that's a force that acts on it.
Pressure?
Specific heat capacity?
Yeah, so specific heat's an example, okay? So a tiny piece of copper and a giant piece of copper have the same specific heat. Density is an example. A bowling ball sized piece of iron or a 3-ton piece of iron, they have different masses, but they have the same density because iron has the same density. So molar mass would be an example of an intensive property. So a tiny piece of carbon or a giant piece of carbon has the same molar mass. Okay, so you can write the example mass and molar mass. Those are good examples of extensive versus intensive properties. So that'll be important when we start doing these calculations, when we look at the energy, to think about if it's dependent on the amount of matter we have or not. So you've all heard about the law of conservation of energy, right? That's not a new thing to you. It says that energy can't really be created or destroyed. We know that's mostly true. But that doesn't always apply to our kind of individual localized situations. So if this room is hot and then we cool it off with the air conditioner, did we lose energy in the room? We lost thermal energy, yeah. But did we destroy that energy somehow? No, we just moved it outside, most likely. Okay. So when we think about energy loss or energy gain, just make sure you know that's not energy creation or energy destruction. Okay. We're just transferring it from place to place. Or the other common thing we can do with energy is convert it from one form to another. So if you think about the little, what are they called, hot hands, the little packets you shake and they get hot. So are those able to produce thermal energy? Can they get hot? Yeah. But when you buy it in the store, is it hot? No. So does it somehow magically create that energy somewhere? No. It has chemical energy that it converts into thermal energy. Okay. So did it really create energy? No. But it was able to convert from one type to a more useful type for our situation. Yeah.
What is the chemical difference?
We'll actually do something pretty similar to it in lab tomorrow. So that's an example of where you might think the law doesn't apply, but it really, we aren't creating or destroying, we're just kind of transferring. So an important, or two important words here when we talk about energy conservation would be the system versus the surroundings. So we used the word system once or twice in the last chapter. Where did that come up? You remember? Yeah, so in the middle calorimetry, when the final temperatures are equal, we say the temperature of the system is 25 degrees. So the system meant the water and the metal block, right? I mean everything. So for the sake of this, we talk about energy in the system. The system is what we're working with, okay? So it's the reactants, the products, the container, the temperature probe, whatever we're using, that is our system, okay? The surroundings is everything else. So if you're doing a chemical reaction, are you a part of the system or the surroundings? The surroundings, okay? What is the major component of the surroundings for all chemical reactions most of the time? Yeah, the air around us. That is what the surroundings are typically defined as, okay? So if energy is released from the system, where's it going to be absorbed by? The surroundings, okay? So when we talk about, just a simple example, if I have a beaker of cold water, my system might be the cold water, the beaker, and the thermometer, and it's going to absorb energy from the surroundings, and in that case the surroundings are is the air, and the air around us, okay? So we use that phrase quite a bit, so just be sure you know the difference in system and surroundings. And system doesn't only refer to the chemical reactants and products, there can be other things involved as well. So then you have the law typed out there for you in words. But in the last chapter, we said that energy and heat are pretty similar things, right? So thermal energy is a type of energy. Okay, so Q is a kind of a subset of energy we have there. So a new word we have is enthalpy. And just to make life interesting, we abbreviate enthalpy with a capital H. Enthalpy, yeah, we used it a couple times without talking about it, so we'll talk about it more now. So enthalpy, you'll define more as you move to higher level chemistry and physics. It's kind of an important concept, but for now, we can think about enthalpy as being kind of the internal energy of the system. Okay, so it's how much energy we have in that system. So we can also say enthalpy is a quantity of, we'll just say E for energy transferred. Okay, so enthalpy looks at energy transferred, gained, or lost during a chemical reaction or chemical process. So if we use it to look at energy gained or lost, I don't care about the actual amount of enthalpy per se or energy. I care about the change. Okay, so what symbol do I have to represent a change? Delta. So what does delta or triangle H mean? Change in enthalpy. So then, the formula for enthalpy, delta H, is very easy. So the delta H, we'll just say reaction. So the enthalpy change for a reaction is equal to delta HP minus delta HR. So what do you think the P and the R stand for? It's not pressure. I heard it. Yeah, products and reactants. Whoever said that? Okay. So let's think about, does that make sense? If I want to see the change in enthalpy during a reaction, I take the change or the enthalpy after the reaction minus before the reaction, and that's my change. It should be logical, okay? We're just looking at the change as we move from reactants to products. Yeah.
Would you have to have the delta H there, couldn't you do the product energy minus the reaction energy?
I mean, you got to have some way of like telling you it's energy. You can't just say products minus reactants, because then products is like the actual chemicals. Yeah. So we talked about in December, November maybe, the 5 major types of reactions. We'll talk about in inorganic chemistry: synthesis, decomposition, single, double replacement. We all remember those? So those still exist. Those are still the 5 major types of reactions. But now we're going to use energy change to classify reactions into 2 categories. So the 2 categories we'll classify reactions into will be they either use up energy or they release energy, either endothermic or they're exothermic. So this doesn't do away with the other 5 types. So these 2 new types, you can be combustion and exothermic, okay, or single replacement and exothermic. So you're both. And this is a new classification system we have based on what they do with energy. So the first type, exothermic, what do you think that means? What does it do? Yeah, it releases, we'll say heat for now. It releases energy. So you have that reaction typed up there. H2 plus O2, my arrows still don't print, makes water. Okay. Nothing new. But then I'm going to write something at the end. I'm going to say plus 483.6 kilojoules. So you already know that what I typed out means 2 hydrogens plus 2 oxygens produce 2 waters, right? That's not new information. But what does that new number that I wrote up there tell me? So is the energy being produced or being used up? Produced. How do I know it's being produced there? Well, it's under exothermic, yeah, but if it weren't under the exothermic category. Yeah, it's on the product side. Okay? So in this example, energy is written on the product side, indicating what type of reaction? Exothermic. Okay? So we react the reactants to produce the products. So if energy is a product, I am producing energy. So the system is producing.
Hi, Mr. Franklin.
Hello?
Can I have Logan Ware for checkout, please?
Let you Logan. Yes, you can.
Thank you.
Okay. I don't know what I was saying. Anyway, okay, so it's exothermic, so energy is being released from the system. So where is that energy going? Into the surroundings, okay? Where do you exist? Surroundings. So what kind of temperature change are you going to see, an increase or a decrease? You're going to see an increase, okay? Energy is released, have a good day, by the system into the surroundings, so you're going to see a temperature increase. Okay, so even though energy leaves, temperature goes up for you. So here's the tricky part. Delta H, which is change in enthalpy here, for the reaction, is it positive or negative? Are we increasing or decreasing the energy of the system? We're decreasing it. Okay, so it's negative. Because we're releasing energy from the system into the surroundings. Okay? And then we can say the negative value just tells me it's. So what's the actual value for this delta H? What's the numerical value? Yeah, so negative 483.6 kilojoules. So it's not written as a negative in the reaction. How do I know to make that a negative? Change the sign because it's on what side? Products. Because it's being released, it's going away. Okay. So we're losing 483.6 kilojoules of energy for every 2 moles of water that we produce. Okay? Make sense? Then it says the formation of bonds is typically exothermic, which is kind of a little fact. And then you have over to the right an energy diagram, or it's a reaction pathway, reaction diagram, I'm going to call it. And all it shows is the relative energy of the reactants in the products. So if energy is being released as you go from the reactants to the products, what is higher in energy, the reactants or the products? Reactants. And we see that. Okay, so here the reactants are higher on the diagram than are the products. Typically the y-axis has no units here or no numbers. It's just to show you which is higher and which is lower. Okay. So just by seeing that diagram, you should be able to tell me the reaction is exothermic, energy is a product, and the delta H is negative. Right? We know those three things just because the reactants are higher in energy than are the products. Okay. Any questions about that? Good. So now let's look at endothermic reaction. So this reaction and this reaction are what? They're exact opposites. So what goes in this blank? 483.6 kilojoules. Fix my dumb arrow again.
Why is it print like that?
Something about the font. I don't know. Yeah, I've got these saved as PDFs, so they're kind of a hassle to change.
When you do symbols, it kind of changes the meaning.
Does it?
Even if you did a star, it would change it, because these little symbols kind of change it.
I usually just type like line, little triangle thing like that, but somebody else type these. So here, I'm doing what type of reaction? Synthesis, single replacement, decomposition. I'm decomposing water. So if I have a cup of water, is it going to naturally break apart into hydrogen plus oxygen? No. What have you got to add to that water to make it do that? Energy. Okay. So the energy is being used to break apart the molecule. So if we're using up energy, is energy a reactant or a product? It's a reactant. So in this situation, energy is on the reactant side. So it makes it what type of reaction? Endothermic.
So do you pretend like the energy part isn't there? So that's not part of the reaction, you wouldn't call that like...
No, you don't really call it a reaction or product, we just write it over there to see.
Oh, so it's not really part of it.
I mean, you have to have it to do the reaction, but it's not really like a physical thing you can hold. So, let's think about this. Yeah.
These equations, are they supposed to be balanced?
No. I mean, they might be.
Yeah, that's what I was...
Are they not?
Because
It's not balanced at all.
Is it part of
The
it?
2 should be with the O2, which is the H2.
You sure? There's 2 O's on the left, 2 O's on the right, 4 H's on the left, 4 on the right.
Oh, wait, never mind.
Now all the virtual students get to hear you ask that question. So, anyway, in this situation, the reaction is a using up or releasing energy. So the system is absorbing energy, right? Where is the system getting that energy? Surroundings. So the surroundings are going to experience what type of temperature change? A decrease in temperature, okay? So if you're taking energy away from the surroundings are going to see a decrease in temperature, okay? So these reactions are kind of weird because we think about reactions as getting hotter, right? We mix two things together, it gets hot. These are the opposite. You do a reaction, it gets really cold, or not really cold, it gets colder depending on the reaction. It's kind of the opposite of what you expect. So here, the delta H, is it positive or negative? It's positive because I'm adding energy to the system. Okay, so if I add energy, it's a positive value. So what is the actual value? 483.6 kilojoules. Do I have to write the positive? No, but I just wrote it there for emphasis. Then I can say the positive value indicates that it is an endothermic reaction. The next sentence should make a lot of sense. Breaking of bonds is normally endothermic reaction. Okay? So if we're breaking bonds, we require energy to break those bonds, right? You have to apply energy. You don't release energy, you apply energy. And so then you have the reaction energy diagram. It's the exact opposite for endo versus exo. You have the reactants, then they increase in energy. And so energy is being applied there to the system, and the products are now higher in energy than the reactants were. Okay. Any questions about those two so far? Before we go on, let's kind of summarize this. Let's turn over to the side. So I can just say a negative delta H for a reaction tells me it's what type of reaction? It's exothermic. So what is higher in energy? The reactants or the products? Reactants. I can say reactants higher in energy. Then the temperature of the surroundings do what? Increase. The temperature of surroundings increase. So could you do that same summary for endothermic? Yeah, they're all the exact opposite, right? Positive delta H, endothermic, products are higher in energy, and the temperature of the surroundings decreases. So go ahead and fill those in. Are those sweet potatoes for us? What kind of sandwich is that? It's an orange.
It's hot.
Makes me feel better about it.
It's pretty good.
So, should you also be able to, just based on one of these diagrams, tell me all of this information? Yeah, because you can use the diagram to figure out endothermic versus exothermic. Then you can tell me all of this other stuff that's going on, okay? So, do exothermic reactions need energy to keep going? So exothermic reactions release energy as they go, they don't need the energy. Do endothermic reactions need energy to keep going? Yeah, they have to have the energy from the surroundings to continue, okay? And we think of exothermic reactions. Think about chemical reactions, you think about like heat and bubbling. But when we talked about the signs of a chemical reaction several chapters ago, we just said a change in temperature. Most people assume you get hotter. Okay, but a decrease in temperature is also a sign of a chemical reaction. Okay, we'll see in lab tomorrow, sometimes temperature decreases pretty drastically when you do a chemical reaction. So now, using this knowledge, we can write what we'll call thermochemical equations. So it sounds complicated, but you already know what a chemical equation is. You've done those. So a thermochemical equation just uses a chemical equation and shows the energy aspect. So these up here are examples of thermochemical equations. It's a chemical equation and it gives you the value of energy associated with it. Either the energy absorbed, I guess I can stay closer to here, keep walking away from a microphone. Either the energy absorbed or the energy released. And we know if it's absorbed or released based on which side of the arrow I write it on. Yeah.
Are we always going to be given the energy?
We'll calculate it in a little while. But for now, yeah. So now, if we know in this situation that 2 moles of hydrogen plus 2 moles of oxygen produce 2 moles of water plus this many kilojoules, could I ask you 15 grams of hydrogen produces how much energy when it creates water? Yeah, that's kind of what we're headed towards. So instead of just using these numbers, we'll look at for a certain amount how much we need. Or for here, we might say something like 15 grams of water requires how much energy to decompose. So we have this standard value, then that varies based on the amount that we're given. So if you look Just flip it, or I'll flip mine over. On the back of the packet, there's this nice, beautiful table with all this information. So there's a table like this, and these are a type of delta H values. And there are other tables as you move through the packet. So these are the tables that we'll use to calculate the values for these thermochemical equations. So we aren't going to be given these numbers always, but we're going to be given a way to figure out these numbers. So what we're going to do in lab tomorrow, let's think about what's going on. So let me find a piece of paper. So we're going to do 3 different chemical reactions. So reaction A, reaction B, reaction C. And what I want you to do is to write a thermochemical equation for the reactions. So this one might be A plus B gives C plus D, whatever it might be, just whatever reaction. And you've got to decide first if energy is a reactant or a product, and then B, how much energy was released. So figuring out if energy is a reactant or a product, that should be the easy part, right? If it gets hotter, you see a temperature increase, is it endothermic or exothermic? Exothermic, energy is released. If temperature decreases, it's endothermic. That's the easy part, deciding that. But the actual value is a little bit harder. But we're going to do all these reactions in water, and they're going to be dissolved in water. So if I have the delta T for water, and I have the mass of the water used, is there a way to find the number of kilojoules that were released? Yeah, I can just use MC delta T and figure out how many kilojoules were released to raise the water temperature by that many degrees. That's what we'll do. Then we'll have a number of kilojoules, and we can divide by the number of moles to get kilojoules per mole. Okay? So some of the ones tomorrow, or 2, will increase in temperature. So they're exothermic, that's what you expect. The one's endothermic. So if you hold the cup in your hand, you'll feel it get colder as the reaction progresses. Okay? So that's kind of what we're going to do in lab tomorrow. So any questions about any of this today? So we got cut short because of the fire drill. So we'll stop here and then go over your last test.